all'evento, quindi qualche istante per permettere alle persone di collegarsi. Dovreste tutti quanti avere la possibilità di ascoltarci. Con me oggi ci sarà l'amico Claudio Maccone, che avrà il compito di introdurre la nostra ospite, la dottoressa Jill Tarter del SETI Institute, che ringraziamo per aver accettato il nostro invito. Questa sera Jill ci parlerà della sua esperienza per quanto riguarda la ricerca di intelligenza nell'universo, nel cosmo, che ovviamente non ha nulla a che fare con gli UFO. Quindi questa era l'introduzione che volevo dire, l'ho detta e quindi siamo a posto. Quindi aspettiamo ancora qualche istante. Ricordo a tutti quanti che è possibile ascoltare la nostra conversazione, l'intervento della dottoressa Tarter direttamente in lingua inglese, oppure se preferite approfittare della traduzione simultanea dell'amico Paolo Attivissimo, dovete scegliere l'opzione italiano all'interno del menu interpreti che trovate al fondo della vostra pagina. Quindi dipende se avete l'applicazione in inglese o se avete l'applicazione in italiano. Se l'avete in inglese la trovate come interpretation, oppure se l'avete in italiano come interpretazione, e poi scegliete italiano. Se volete togliere anche il background dell'audio originale in inglese, dovete selezionare silenzia audio originale. Nel frattempo che si collegano tutti quanti, io direi che è il caso di sottolineare l'importanza di questo incontro, un incontro che stasera completerà il ciclo di conferenze sul SETI, che è stato iniziato qualche settimana fa, un paio di settimane fa, dal amico professor Claudio Maccone, che ci ha parlato di EvoSETI, e stasera si conclude con la conferenza della dottoressa Jill Tarter. L'evento è organizzato da ASIMOF, l'Associazione Italiana Modelli Fedeli, e dal gruppo Astroteam Le Pleiadi, che è stato fondato da sottoscritto assieme agli amici Alberto Villa, Antonio Giudici e Corrado Pidò di AAV, GAV e APAN, e con anche la partecipazione dell'Osservatorio Astronomico della Valle d'Aosta. In particolare l'Osservatorio Astronomico della Valle d'Aosta, che ringraziamo per la collaborazione, organizza a metà luglio, dal 12 al 16 luglio, la scuola estiva di astronomia presso la sede di San Bartolomé in Val d'Aosta, e quest'anno la scuola è dedicata all'astrobiologia, visto che fra l'altro cade quest'anno il 60° anniversario della formulazione delle equazioni di Drake, che è stata quindi fondata esattamente nello stesso anno in cui il primo uomo è volato nello spazio, con la Vostok 3K di Gagarin, e quindi siamo perfettamente in tema. Volevo anche anticipare a tutti quanti che il prossimo incontro, che è programmato per l'inizio di luglio, vedrà la presenza di un altro scienziato importante, la dottoressa Elizabeth Tarter, che è il Principal Investigator di una delle più grandi e importanti missioni dei prossimi anni, che è la missione Dragonfly, e che porterà un drone a volare su Titano. È una delle missioni più interessanti che la NASA e il JPL stanno organizzando, e avremo la possibilità di saperne di più direttamente parlando col Principal Investigator Elizabeth Tarter. Quindi un altro grande evento che ASIMOF sta organizzando all'interno della serie Un venerdì fra le stelle. Direi che tutto quello che dovevo dire l'ho detto. Stasera ho il piacere anche di avere ospite un ingegnere, perché la dottoressa Tarter è anche un ingegnere, oltre che una delle più grandi astronome del nostro tempo, e direi che è il momento di passare la parola all'amico professor Claudio Maccone per una introduzione alla professoressa, dottoressa Tarter. Grazie a tutti e buon ascolto.
Thank you very much, Dario. And thanks very much indeed to you, Jill, for joining us tonight here and in the afternoon, your time. This is the first time that we can organize...
Recording in progress.
This is the first time that we can organize such a meeting, and we appreciate your cooperation very much indeed. Thank you. So I'm now going to read a short bio of you. Of course, your true bio would be too long to be described in a single installment, but let me go ahead. So first of all, Dr. Jill Cornell Tarter is the Emeritus Chair for SETI Research at the SETI Institute in Mountain View, California. And she serves as a member of the Board of Trustees of that institution. Tarter received her Bachelor of Engineering Physics degree with a distinction from Cornell University and her master's degree and a PhD in astronomy from the University of California at Berkeley. She has spent the majority of her professional career attempting to answer the old human question, are we alone? By searching for evidence of technological civilizations beyond Earth. She served as a project scientist for NASA's SETI program, the High Resolution Microwave Survey, and has conducted numerous observational programs at radio observatories worldwide. She is a fellow of the AAAS, the American Association for the Advancement of Science, the California Academy of Sciences, and the Explorers Club. She was named one of the Time 100 most influential people in the world in 2004, and one of the Time 25 in Space 2012. She received a TED Prize in 2009, 2 Public Service Awards from NASA, multiple awards for communicating science to the public, and has been honored as a woman in technology. She was the 2014 Jansky Lecturer and received the Genius Award from Liberty Science Center in 2015. She served as president of the California Academy of Sciences in 2015-16. Asteroid 74824 Tarter, formerly called 1999 TJ16, has been named in her honor. In 2018, she was recognized with the Maria Mitchell Woman in Science Award and the Sir Arthur Clarke Innovators Award. And in 2021, she was elected to the American Academy of Arts and Sciences. Since the termination of fundings for NASA's SETI program in 1993, She served in a leadership role to design and build the Allen Telescope Array and to secure private funding to continue the exploratory science of SETI. Many people are now familiar with her work as portrayed by Jodie Foster in the movie Contact. Her biography, Making Contact, was written by Sarah Scholes and published in 2017. So this is as little as I could say about Gilles. And again, I thank you very much for joining us tonight. Please, go ahead. The floor is yours.
Thank you, Claudio. Since you have been so kind with your introduction, I can skip this Who Am I slide. And let's just say that I'm chief cheerleader for all things SETI. So before we begin to talk about them and finding them, I'd like to put us in context. So where are we? When are we? It's simple, right? We're here. And for me, as I think for most of you, that's meant a year of working from home, locked in. In my case, it's in this house here in the Berkeley Hills, in the San Francisco Bay Area. And from the altitude of low Earth orbit, we understand that we're here on the west coast of the US. And since 1968, when astronaut Bill Anders took this Christmas Eve photo of Earthrise, we've been able to envision ourselves as here. This is our first opportunity for a truly cosmic perspective. It changed how we see ourselves, and it became an emblem of the environmental movement. And in the summer of 2013, the Cassini spacecraft, which was orbiting Saturn, looked back and saw us here at that little tiny white dot at the end of the arrow. That's all of us. That's us. We're here. And long before that, in 1990, the Voyager 1 spacecraft passed by Neptune and turned homeward to image us here as this pale blue dot in a sunbeam. And we're here in the boondocks of a large spiral galaxy far from the center. Our sun is one of about 400 billion stars in the Milky Way galaxy. And no, this is not an image of the Milky Way galaxy, since we can't get outside of it to take such a picture. It's an image of a large spiral galaxy that is what we think the Milky Way would look like if you could go take such a picture. And indeed, by using radio telescopes and looking at methanol and carbon monoxide gases surrounding newly formed stars in the Milky Way, we can actually map the Milky Way from the inside out. And so after 5,000 hours of radio telescope observations, this is the recently published and best estimate of what the Milky Way galaxy would look like from a distance. And our Milky Way galaxy is here, right? Only one of about 200 billion galaxies in the observable universe. The fact that some of these galaxies are smaller and fainter than others makes us remember that as we look farther out in space, we're looking farther back in time. And so we're now. That's our time, we're now. But we need to relate this to a larger framework. We have a very limited sense of time, and we are actually intimately connected to faraway places and faraway times. So let's start by considering humans and our history, right? Our perspective must encompass that we are now in the current epoch of the universe's 13.8 billion year continuing evolution from the Big Bang to big brains and beyond. And we're not yet completely comfortable with this larger context of here and now. We have, in fact, only directly observed about 4% of the total matter energy density of the universe. And cosmologists struggle with dark matter, dark energy, and gravity itself. Because at the smallest scales and the earliest times, it's not yet possible to reconcile quantum mechanics and gravity. Still, this is the most self-consistent perspective of here and now ever assembled. One that for sure will be subject to future corrections. So now let's start with our human history, right? We humans trace our lineage not just back through the centuries of our families, and not just back through the millennia of human civilization with its art and its many experiments with governance. We trace our heritage not just back over the millions of years since we branched off from the great apes, not just back the 2.4 billion years during which the Earth's atmosphere has been perfused with oxygen thanks to the photosynthetic labors of cyanobacteria. Not just back to the formation of the sun and our solar system 4.6 billion years ago. We have to go back farther, a few million years, beyond that, to a great giant molecular cloud contaminated by the winds of Wolf-Rayet stars and debris of supernova explosions and radionucleotides from neutron star collisions. You see, the iron atoms in the hemoglobin molecules of your blood and the calcium in your bones and teeth, these elements were all fused, literally cooked up, deep within old massive stars that ended their lives in catastrophic explosion. We call them supernovas that blast off the outer layers of the star, leaving behind remnants like this recent example, remnants that became incorporated into our solar system, just as this supernova remnant will be incorporated into a future generation of stars and planets, and perhaps life. So from this perspective, it actually takes a cosmos to make a human. You owe all that you are and everything that around you to nucleosynthesis, the cooking of heavier and heavier elements from simple hydrogen that took place in the heart of long dead stars that blew up at the end of their lives. You are literally made of stardust. And if we're really intent on looking for life beyond Earth, and that's what astrobiology is all about, it seems to me that we should be looking for both biosignatures and technosignatures. We're trying to find inhabited worlds through the actions of the inhabitants. So there are three ways that we could discover life beyond Earth in the 21st century. And I think the odds that one or more of these strategies will pay off is high. We could directly discover it, we could detect its work product, or we could export it. So when attempting to find evidence of life beyond Earth, we're forced to think about ourselves in a much larger context, a cosmic perspective. And I'm hopeful that you will leave tonight having internalized your own cosmic perspective, because that could be the first step along a path to solving the global challenges facing our world today. So we can look for biosignatures. And for the past 5 decades, NASA has been discussing missions capable of finding life by looking for biosignatures, the chemical fingerprints of life, on planets and moons of our own solar system and in the atmospheres of exoplanets, planets orbiting other stars. The Viking lander on Mars was the first and showed us just how hard this would be. There are now a number of ground-based facilities and space-based missions on the drawing board to look for biosignatures. And the upcoming report of the Decadal Review of Astronomy and Astrophysics for the 2030s will have a great deal to say on that subject. At the moment, we can only say that telescopes capable of imaging exoplanets and spectroscopically examining their atmospheres will be big. They can't do their job otherwise. A lot of research is going on within the astrobiology community to understand what might be the best candidate biosignature and how to interpret that and recognize false positives. There's a great deal yet to be known, and at the moment, we have no smoking gun. Indeed, biosignatures may well be ambiguous, and we will want to have as much environmental and historical context as we can arrange in order to draw conclusions. Take, for example, the recent report of the discovery of phosphine in the cloud layers of Venus. First of all, it's a single line detection, so the molecule may not be correctly identified. And then, have we really considered all the chemical pathways and networks that might be appropriate to phosphine production? On Earth, we only find phosphine in anaerobic environments, and biology is the source. So here, close to home, in the clouds of Venus, we're already encountering this ambiguity. We're currently planning on space missions to fly through the cryovolcanic plumes escaping from the cracks of the moons of Europa and Enceladus. How will we be able to unambiguously decide that any molecular fragments that are found are due to biology and not just organic precursors? Ambiguity may be reduced if we decide to look for technosignatures. There are three ways that, we could detect the work product. That is, we could find evidence of someone else's technology that's modifying its environment in ways that we can remotely sense over vast distances. Or we might make a serendipitous observation of some vast engineering, astroengineering project. Searches for technosignatures face the same problems as searches for biosignatures. They must deal with false positives and the difficulty of conceiving and building instruments to find what we don't yet know. Despite these difficulties, this type of research absolutely belongs within the portfolio of searches for life beyond Earth. There could be two kinds of deliberate signals that we should be trying to observe. They could be almost natural or obviously engineered. An example of an almost natural signal would be a pulsar that changed its period and then changed back again. Right? We would find it in our normal astronomical search for pulsars, but we recognize that there's something very different about that particular pulsar. We could also think about looking for transits in front of a star by objects that aren't spherical. Now, the IAU tells us that a planet has to be spherical, so its shadow on the star will be circular. But other types of objects, other shapes, would provide information in the light curves, at the high orders, at ingress and egress, that could distinguish something that was non-round. And lastly, we can think about variable stars, such as the Cepheid variables, and we could build an orbital neutrino factory or some other energetic source and orbit around one of these stars. It will expand and then contract and expand and contract. And in the contracted stage, prematurely, before it's ready to expand, we could zap it with a beam of energy and cause it to expand early, and therefore change the pulse rate. And so you could imagine this like being a Morse code. You'll have the regular pulse period, and then you'll have a shortened pulse period. And that could be a 1 and a 0. And these sources are visible all the way to the Virgo cluster of galaxies. So you could have a very bright omnidirectional transmitter with this idea. All right. Now, for the obviously engineered signals, which we probably would not pick up in our normal astronomical observations, we can consider frequency compression. So signals that don't spread in frequency the way nature does because of the movement of different atoms and molecules relative to one another, but just a single frequency on the dial. We could also consider time compression, so nanosecond pulses in time that we don't think that nature can make. And lastly, we can consider looking for monochromatic laser signals that might be used, for example, to accelerate spacecraft, like this example here of Starshot project. And the difference between these different modes is important because the astronomical consequences, observational consequences, are that we should do astronomy of all different kinds with all different new instrumentation, opening up new phase space that hasn't been explored before, and perhaps we'll find evidence of technology. But for the obviously engineered signals, we need to conduct systematic searches for what we're thinking about, and we're going to inevitably have to build dedicated telescopes because we're looking for things that aren't astronomy, so astronomers aren't going to build these instruments for us. So lastly, as we look for life beyond Earth, we can think about exporting it. We're going back to the moon. We have ambitions to go to Mars, perhaps visit the asteroids. And there are studies like Breakthrough Starshot and the 100-Year Starship Study and Project Icarus that are looking at ways where we might take life beyond Earth. So I like to give talks like this. I like to talk to groups such as yours, because I think in talking about life beyond Earth and how we might find it, the process actually holds up a mirror that shows us all on Earth to be the same rather than different when we are comparing ourselves to someone that may have evolved on a different planet or orbiting a distant star. So this concept of a cosmic perspective trivializes the differences among humans. And it's very important because we have challenges today on this planet which are going to require global solutions. These challenges do not respect national boundaries. we're going to have to figure out how to organize and cooperate globally to find solutions. And so it's really a good idea to begin thinking of ourselves as Earthlings rather than Italians or Americans or Canadians or Brazilians or any other nationality. We are all Earthlings, and that's a very important perspective to hold. So Caleb Scharf has this lovely quote, "On a finite world," and that's certainly where we live, "a cosmic perspective isn't a luxury, it's a necessity." And I think that if I do nothing else than try and make Earthling a meme, I will have done a lot of good work. And so I would ask you, when you get back to your devices and you look at the profiles that you've embedded about yourself, that you go and change those profiles so that the first thing you say about yourself is that you're an Earthling, and then try and act that way. So we are beginning to do larger and larger radio and optical searches for somebody else's technosignatures. And for the first time, now we have sufficient compute power to think about looking for signals that are transient. And then we have to think about, how do we build confidence in looking for those signals? Because if they're not there when you, after the fact, go back to try and re-observe them, reacquire them, then how can you have any kind of confidence in what you've actually found? And as Carl Sagan reminded us, extraordinary claims demand extraordinary evidence. And so how do we begin to do our observing in a way that we can have confidence, even if the signal is fleeting? And one way to do that is to observe with more than one telescope, right? Or multiple beams from the same telescope. And then as more and more beams detect this transient phenomena, then you can have more and more confidence, right? And so for that reason, I think that the best instrumentation for looking for transient SETI signals will be arrays of one type or another. Because with an array, you can add the incoherent power from all of the telescopes to do a detection quickly and with minimal computation. And then you can pick a threshold and say, all those events and sources where my incoherent power exceeded that threshold are going to be good targets for me to try and correlate the data to make an image on the sky. RFI interference will not correlate, but a real signal moving at sidereal rate on the sky will give you an image that is essentially a beam pattern. And so as we move forward into this new era of incorporating transient signals into our search, I think it's really important that we, A, co-observe with multiple telescopes, and B, think about using correlation techniques to distinguish between our technology and someone else's. So that's my last thought for the evening. Thank you very much for listening. And I'll stop sharing my screen now.
Okay, great. Thank you very much. Thank you for this very interesting speech. And I ask to the audience to put their questions on the chat. But I don't know if Claudio would like to say something or place the first question to Jill. Otherwise, I will start with my personal question to you, Jill. And my question is, why SETI? Why at some point you decided to dedicate most of your scientific time and efforts to this wonderful search for existence of intelligence outside our Earth?
Well, for me, it was just a very fortunate accident. Right? My first year as a graduate student at Berkeley, I was supported to program a PDP-8/S computer. Now, it's the first time that we'd ever had a desktop computer, and it took two of us to get it up on the desk, but it was still a big improvement over these large, massive compute centers. So that computer had no language. You had to program it in octal. So you had to set all the ones and zeros to do the 11 instructions that that machine could do. And I did this. I thought it was great fun my first year. And then I went on to other things. And that machine, many years later, when I was still a graduate student, about getting ready to leave to do a postdoc, that machine was given to an astronomer, Stuart Boyer, an X-ray astronomer who sadly we just lost this year to COVID-19. And he had a very clever idea. He said, you know, University of California at Berkeley has a radio telescope at Hat Creek. And because it's radio and you measure both the amplitude and the phase of a signal you receive, you essentially can make an infinite number of noiseless copies of the signal. And so the astronomers who are pointing the telescope and selecting the frequency, they can have their data, but we can make a copy of that data and we can analyze it for engineered signals, right? Very clever idea. We call that commensal observing today. And so Stu didn't have any money, so he went borrowing and begging equipment, and this PDP-8/S computer got given to him as surplus. And he said, what do I do with this? And somebody said, go down the hall. Jill used to program that, and maybe she still remembers how. So he showed up at my doorstep with a copy of the Cyclops Report, which was an engineering design study that had been done at NASA Ames Research Center and Stanford Engineering. And it was how to build an array of 1,600 100-meter dishes to look for evidence of someone else's technology. And I was startled, and I was really, I thought, well, I read the Cyclops Report and just was amazed that I had the right skill sets and I was in the right place at the right time. And I just got hooked that this old question of humanities was something that we could stop asking the priests and the philosophers what we should believe and begin to let engineers and scientists actually take a look and see what's actually out there. So I thought, well, I'm hooked. This is what I'm going to do. And that's a long answer to your question, but that's how I got into SETI.
Incredible. Fantastic. Thank you very much. So, again, Claudio, are you online?
Yes. Well,
okay. I'm sure you have a question for Jill as well.
Well, first of all, I have a comment. Jill, you mentioned the Cyclops report. Of course, this is precisely the same thing that converted me to SETI. For me, the story was different in that, I had done a PhD in mathematics at King's College London. So my background was different. As you know, now I had been working on the KLT, which is a principal component analysis of signals that at that time was not really used in SETI, but later became used. So the story is slightly different, but nevertheless, let me say that when I discovered the Cyclops report, that was a real revelation for me. You know, I could hardly believe that such a jump had occurred in the mind of people involved with SETI. And apart from that, in 1985, I read the famous novel Contact, which is about you, obviously. and that was one more reason why I became interested in SETI. Let me just remind you and all the people listening to us that you and I met for the first time, as you probably remember, in 1987. That was, I guess, January 14th. And the reason was that I made my first trip ever to California, visiting, of course, NASA Ames Research Center, where you were working on SETI. At the time was still NASA SETI. And I gave a mathematical presentation of the KLT. And I have to say proudly that there were only 3 people that seems to be convinced that the KLT could be of some use for SETI. You were, of course, one, and the other one was Ken Callas, that you certainly remember, and the other one was Ivan Linscott. And just to be precise, unfortunately, certainly I could not convince Barney Oliver because he has, you know, I mean, you know him, you knew him, and so he had a different background. He thought that the Fourier transform was the best possible algorithm, and that was it. But nevertheless, it was really a great beginning, Jill. And after that, we have been in touch, and I thank you very much. Actually, I guess the Stelio Montebugnoli is also connected to this video conference. And you probably remember that many years in the past, Stelio and I were sitting in the room of the SETI committee meeting that you were dominating because you were the chair, of course. And you know, for us, coming from not only from outside the United States, but also from outside the main SETI business, it was such a honor to meet with all the people from Berkeley and from the SETI Institute that were doing real SETI. So I thank you very much about all this. Good remembrances. I didn't write yet a sort of autobiography as you did actually, but if I still have time, I will try to do so, and I will thank you enough for your initial support. Thank you so much.
Thank you, Claudio.
Okay, Jill, if you still have a few moments to share with us.
I have a few more minutes, but I do have a commitment at the top of the hour.
Okay, just let us know when it's time to close. Just let me translate a few questions from our audience. The first one is coming from Maurizio, asking if the SETI at home projects will be restarted sooner or later. Do you know anything about that?
Well, that's a project that's being run by the Berkeley Center for SETI Research. I'm not sure. I think that they're more eager to do new things. But again, it's not my project, so I can't say. Okay.
Another question is coming from Armando, and is asking to you, what do you think about the Fermi paradox and how the discovery of intelligent life would affect our life in the future?
Well, I don't think that there is any paradox, right? Basically, the Fermi paradox says that if ever, anywhere, and any when there was a technological civilization, that we should have seen them by now. And since we don't see them, that means there never can have been any civilization like that, and we're the first. But I don't think you can make the statement that we haven't seen them, because we've hardly begun to look, right? We haven't done systematic searches. We haven't done significant searches yet. So you can't say they're not here. You can't say we haven't found them, because we've hardly begun to look. So I don't find that paradox very compelling. I like to make an analogy that if you take all the searching that we've done since Frank Drake's Project Ozma, and it's a 9-dimensional space that you have to explore, and you kind of figure out what the volume of that space might be before you could be successful, then given what fraction of that volume we've searched to date, it's like we've taken one glass of water out of the Earth's oceans and examined that and haven't found anything. And I don't think you can draw very strong conclusions yet from that.
Okay, just a quick question from Morando. Who's the historical father of the SETI research, according to you? Is it Frank Drake or somebody else before him?
Well, Cacconi and Morrison and Drake all came upon this idea in 1959, 1960, began thinking about it and writing it. So I think it's kind of a triumvirate.
Okay, thank you. Another interesting question from Marcello is, considering our humans' current technology, if we put those technologies on a planet orbiting our closest star, Alpha Centauri, for example, will they be able to detect life on Earth and see us from there?
Well, it depends on what the transmitter is. If you say our most prevalent transmitters at the moment are TV transmitters or radars, no, that there's just not enough power there. If you ask how far could you see the most powerful transmitter that we've ever had, which was the Arecibo planetary radar, yes, then you could see that very easily. But of course, it had to be pointing at you for you to discover.
Yeah, of course. And then a question about the Oumuamua asteroids. From Pierluigi would like to know if there is any possibility about artificial origin of this.
Well, certainly some people have speculated about that. All of us who read Arthur C. Clarke's Rendezvous with Rama got that thought when we first discovered this. And we've observed it with the Allen Telescope Array. Berkeley's observed it with the Green Bank Telescope, looking for engineered radio signals, and we didn't find any. So I think what's going to answer this question is, now that we have tools, optical tools like Pan-STARRS telescope, that can in fact detect these things, and that's a new capability, what their frequency is in the future. We should be detecting lots more of them. And if the frequency is really high, then I think that you are going to be forced to an astrophysical explanation. If in fact we hardly ever see another one again, maybe a technological solution makes sense, and we just didn't look at it in the right way when we had the opportunity.
Yeah, you're right. And then we need also to consider that for us human beings, we are at the beginning of this technological development. As we know, we just invented the radio frequency communication systems since a little bit more than 100 years, from Guglielmo Marconi activities, Henrik Hertz, and the others. So the technology will evolve quickly, and we will start to be more capable of detecting intelligence signals in the years to come, if we will not destroy ourselves before. Okay, Andrea is asking, he would like to know your personal feeling when you saw the Arecibo radio telescope collapsing a few months ago. What does it mean for the SETI research?
Well, in 2004, we left Arecibo in order to put our funds into building the Allen telescope array so that we could be on the air all the time. Nevertheless, I spent so many hours observing at that telescope and marveling at the engineering construction that it just was heartbreaking to see that telescope collapse. And I hope that there are enough funds in the scientific community that we can look at building some appropriate replacement. Might not be the same kind of structure at all, but something that's scientifically as useful in so many different ways as that telescope was.
Okay, so if you still have time for a couple of questions.
I have about 3 minutes.
Okay. So our friend Giuseppe is asking if a part of listening to signals coming from the cosmos, do you think we are going to send again some signal outside as we did 30, 40 years ago?
Yeah, there have been a couple of other examples of transmission as well, and it's called METI, messaging with extraterrestrial intelligence. My own personal opinion, and that's all it is an opinion, I think we're too young, right? I think if you're going to transmit, you need to be able to commit for long time periods of transmission. Because if you transmit for 5 minutes, that signal is going to go past your target in 5 minutes. And if they're not looking in exactly the right way, at exactly the right time, they'll miss it. So transmission, to have much chance of being detectable, needs to be a long-term commitment. And at least in the US, we can sometimes do 5-year plans, but nobody's tackling a 10,000-year plan except religions. So we need to grow up and become a much more stable technological civilization that can, in fact, take on these long duration projects.
Yes. Okay. From Alien, there is a question. Would like to know if you can point us to one specific signal that we detected so far you think it worth investigating more, or it was interesting for you.
Yeah,
probably it was mentioned to WOW signal, something like that.
Yeah, well, the WOW signal was strong, but it didn't actually meet the criteria that the experimenters had set up to say this is an interesting signal, because it only ever showed up in one beam and never got into the other, and I would have never talked about it. We've had false positive signals that have kept us confused for better part of the day, because we do our signal we did our signal processing in near real time, and so we knew we had something, but what it was and whether it was really coming from the direction on the sky the telescope was pointing was something that we couldn't quickly discern, because the second telescope that we were supposed to be using had gotten hit by lightning and we'd lost a disk drive. So for a couple of days, we are down just to one telescope pointing on and off and on and off, and it's unambiguous. I mean, it's, sorry, it is ambiguous sometimes. And it turned out for us that it was the SOHO spacecraft in orbit around the sun, not around the Earth, that we had in, it fell into the side lobe of the telescope. And all those hours, every time we moved to the same position on the sky, that signal came back in the side lobe. It wasn't in the main lobe at all. So I know we were disappointed. We were excited for a while. And when you get excited, you make silly errors. But it didn't turn out to be someone else's technology. It was our own. And I think that's it for me. I've got to go on to another appointment. Thank you again for hosting this and for having me.
Thank you very much. Thank you very much, Jill. Thank you for being with us. Thank you for spending time with us. We learned so much tonight from you, and we really appreciate the big time and efforts. And thank you for being so involved on this fantastic research. And thank you for spending most of your time helping us to learn about ourselves first and learn about how fragile is our planet. And you're right, we are all human beings living on Earth before being Italians, Switzerland, and Americans. You're perfectly right, and we will follow your advice. Again, thank you, and hope to see you soon in person. Thank you, Claudio. Thank you very much to Paolo Attivissimo for the translation. A big applause. Bene. Grazie mille, Alberto, Vittorio, Paolo, voi che potete smutarvi.
Terminiamo la registrazione. Ciao.
Eccomi.
Eccoci.
Allora, com'è andata? Tutto bene?
Benissimo. Cos'è successo?
Bene, bene.
Non mi vedo più, vabbè, tanto sono al buio.
Recording stopped.
Sì, allora qualcuno ha interrotto la registrazione. Adesso aspetta, Dario, ti sei spento la telecamera. Ti mando io la richiesta di attivazione. E adesso ti si vede, ma perché sei così al buio? Cosa fai lì?
Sono fuori, ma sta arrivando il temporale. Non lo so, è diventato buio di colpo. Vabbè, sono extraterrestre stasera.
Ma infatti hai gli occhi blu e quindi ci fai paura, insomma.
Sì, è un po' più inquietante del solito, devo dire. Allora, c'è Paolo Miniusi che chiede se riusciamo a leggere le sue domande qui. Sì, riusciamo a leggerle, Paolo, però non lo vogliamo fare, perché siamo cattivi dentro. No, scherzo. Sì, le riusciamo a leggere.
È vero, ho gli occhi blu.
Sti extraterrestri, te ne
ecco,
sull'altra.
Ecco, vedi, come al solito, quando si illumina bene la scena, ci si rende conto che non sono extraterrestri, ma sono cose assolutamente normali.
Certo.
Beh, assolutamente
non sono
normali.
Neanche extraterroni. Però...
no, ma non devi dire queste cose.
È una battutina, dai. Tanto...
ho capito.
Non ci ascolta nessuno.
No, guarda che siamo ancora in diretta,
Sì, vabbè, ma voglio dire...
Vi chiedo scusa, guardate che su Italiano non vi si sente. Io adesso ho disattivato per sentirvi. Eventualmente magari passate su Italiano, se no non sente niente nessuno.
Allora, aspetta che faccio un annuncio. Se volete seguire il fuori onda, se mi sentite, se volete seguire il fuori onda, vi chiedo di passare al canale normale, quindi di non scegliere più il canale italiano, ma di scegliere off, disattivato, che è la prima opzione nel menu interpretazione. Così magari ci sentite perlomeno, e per alcuni di voi ci vedete anche.
Perfetto.
Ah, ok. Eccoci qua. Insomma, sempre fonte di altissima ispirazione, Giro, quando ci racconta la sua esperienza e soprattutto la sua visione di quella che è la ricerca della vita. Mi è piaciuto molto anche la risposta alla mia domanda su perché il SETI, ed è stata proprio un'esperienza legata alla sua capacità di programmare questi PDP 9, P11, questi agli albori della scienza dell'informatica, i primi calcolatori in assembler, in codice binario. Vedi, cioè, quindi la sua anima ingegneristica di ingegnere programmatrice ha portata a imbarcarsi in questa avventura che poi l'ha vista crescere chiaramente a livello mondiale negli anni. Bene.
Ok, scusa, posso stoppare la registrazione mia?
Sì,
anche?
sì. Sì, stoppiamo tutto. Sì, sì.